Okay, recording. Go.
Hello, my name is Kareem and I'm a technical account manager with MemSQL. I've worked here for a year and a half and have been working primarily with Oracle before for 13 plus years. In the last 100 years, there have been a handful of health crises that have been labeled as a global pandemic, and they have been typically spaced out throughout the century. I wasn't in the USA during the last declared global pandemic, being the swine flu of 2009, so I can't comment on how things have been here and how the turndown felt like. However, I have been living here since they declared the novel coronavirus or COVID-19 as a global pandemic and have been also living here well before then. I, as many Americans and other people around the world, can attest to the catastrophic effects that COVID-19 has had on our economy. There have been declared travel restrictions almost all around the world, plus self-quarantine and or self-isolation restrictions in big parts of the world, as well as most of the US. Things have been as bad as having curfews in parts of the US and in the world. There have also been the need for social distancing, which have proved to be effective in slowing down or stopping the spread of the virus. Social distancing meant that we close or shut down most sit-in restaurants in the country to avoid the spread of the virus among diners, plus closing down any events where it became impossible to maintain social distancing. That includes festivals, Olympics, concerts, and all the big sporting events. The economy has come to a standstill and millions of jobs have been lost due to the closures. For that, countries started looking at two things, flattening the new cases curve to stop the spread of the virus, and once under control, keeping the curve flat while trying to gradually open back the economy. A few challenges introduced themselves, which became major bottlenecks when thinking of reopening things back up. Let's discuss those challenges in the next slides. I think the main challenge was reopening the economy is what we've been calling as contact tracing. What that means is tracing or tracking down all the people that might have been exposed through contact with someone who has tested positive for the virus. One of the major challenges with a contagious virus like COVID-19 is the ability to be transmitted from someone who shows absolutely no signs or symptoms of the virus, but then being later tested as a positive carrier of the virus. So we have symptomatic people who simply stay home because they feel sick. Those are the ones who have shown clear symptoms of the virus, and we have others who show no symptoms of the virus whatsoever, but are carriers of the virus and are wandering outside their homes freely. They actually could potentially transmit the virus to almost everyone they come in contact with, and that's what contact tracing really means. It's the backtrace of everyone who has come in contact with the asymptomatic COVID-19 carrier over the last 14 days. Another avenue of contact tracing is also tracing contact between people who are not maintaining social distancing or people who are clustered and gathered in numbers that make it so difficult to maintain social distancing and accordingly increase the risk of transmission of the virus. So to recap, contact tracing is about backtracing of potential patients who have come in contact with someone who has tested positive for the virus, and then asking those potential patients to self-quarantine or self-isolate for 14 days. And also contact tracing is identifying any social gatherings or clusterings that are making it easy for the virus to spread. So now that we've talked about the pandemic and its effect on the economy and what's really needed to flatten the curve and keep it flat while we attempt to reopen the economy, let's talk in the next few slides about the hurdles that exist that make contact tracing so difficult or challenging. We now understand what contact tracing is and how it helps flatten the COVID-19 curve. Let's touch on how contact tracing is typically conducted and what it really entails. The process of human contact tracing as it exists today is done through almost 12 hours of interviews per patient to really try to backtrace whom they have become in contact with during the last 14 days. People don't typically record in their heads whom they have used a doorknob before or after, or whom they might have used a shopping cart before or after, etc. Also, if that person is typically very active due to their activity nature or the nature of their job, then this becomes much more challenging, hence the 12 plus hours of interviews that are required to do this. What if we have hundreds of thousands of positive COVID-19 cases or even millions? That means we will need hundreds of thousands of human traces and maybe millions of hours to properly conduct the historical contact tracing for asymptomatic cases, which still might not be 100% accurate. Additionally, without an enforced stay-at-home curfew, which is not possible or feasible in a lot of countries, it becomes as challenging or difficult to identify clusterings of people who are not maintaining social distancing. Having said all that, we all know that automation exists everywhere around us, which is simply automating repetitive processes or jobs that can be done using a computer instead of wasting precious human hours that can be invested and used elsewhere. Also, computer or technology automation is usually more accurate than human intervention, especially for error-prone activities. But then the question is, what can we use to automate the process of contact tracing? Can we use computers to conduct those 12 hours interviews? I think the answer can be much simpler than this. We take our phones with us everywhere, and so our historical location is always known to the telecommunication provider. It has a long retention period for billing purposes as well as network quality purposes, ads, etc. So let's discuss in the next few slides about how we can use our phones for contact tracing and to also triangulate or identify clusterings of people or groups who are not maintaining social distancing. A lot of the telecommunication providers or mobile operators across most, if not all countries, are using the mobile phone's geospatial locations for running reports to understand the signal quality, the usage trends of the user, etc. They can also use the same location information for sending relevant ads, local weather, and law enforcement alerts, and so on. Additionally, a lot of health departments around the world are creating a big data store of all the positive COVID-19 cases with details on the patients, their symptoms, their special circumstances, etc. Most of those health departments would probably be using a cloud provider of some sort to store this information, because if you think about it, we're talking about petabytes and petabytes of data, and it's usually not very reasonable to archive such accounts of data in a localized data center for high availability, secrecy, as well as cost purposes. Combining the telco location data with the health department's patient's data can generate a very powerful tool for contact tracing that can ultimately replace the human tracers and allow the contact tracing capabilities to scale beyond human limitations, which will accordingly expedite the reopening of our economy. The telco location information can also be used for directing vaccination efforts, sending ambulance to patients, and things like this. If we can somehow build a system that correlates the location data of the mobile operators with the patient's data from the Department of Health, and identify where those patients have been for the last 14 days, then we can easily generate a report of whom they might have contracted the virus to. That happened through contact or other means. We can also use the same location data from the telecommunication providers to identify the clusterings of people in hotspots or locations and mobilize the local law enforcement to guide them into disbursement for their own safety and well-being. The concept is very simple if you think about it, but the execution is far more complicated. The solution that can be optimally used for this purpose has to be extremely performant and reliable because it can save lives, and accordingly that means that there are unique technical requirements to be met that we can discuss in the upcoming slides. The set solution needs to consist of some main components. First of all, it needs to consist of an alerting and visualization dashboard that can be used for multiple things. It will be used by tracers to be able to drill down on user locations and identify their contacts over the past 14 days. And it can also be used for alerting whoever needs to be alerted when clusterings of people are happening that are against the social distancing guidelines, especially for hotspot locations or areas where the virus has already spread. In addition to the dashboard, the solution needs to be able to ingest real-time decisions, to be able to ingest location data of millions of users in more seconds, to be able to make real-time decisions possible, which can save lives and reduce the spread of the virus. Also, the solution should allow the same real-time decisions or analytics to run against live location data as well as historical location data. And as explained, the historical location data can run in the petabytes in size, and a lot of cases would need to be joined with the live data that's being ingested into the system to identify the patient's recent and not so recent contacts based on their symptoms and how far they are with the contraction of the virus and so on. Finally, the solution would have full support for geospatial data as well as full analytical capabilities against the same. The data store part of the solution will essentially be built using geospatial data types, and the accessibility of this data needs to happen with very low latency and a very high level of concurrency. Reason being is that while the new location data is being ingested into the data store, aggregations and analytics will be running in conjunction with pre-existing data that needs to happen at very low latency for millions and millions of mobile users, hence the high concurrency requirements. Last but not least, the solution needs to be simple enough that it can be implemented and scaled in weeks and not months. Let's provide a potential or sample architecture of what the solution can look like in the next slides and touch more in the data store part of the solution, being MemSQL and its capabilities. Obviously, this solution can change based on requirements, but the fundamental concept stays the same. The data store that needs to be used for this should have unique capabilities, right? It needs to provide full geospatial support to enable the manipulation and analysis of the geospatial location data. The architecture of the data store also needs to be one that supports lock-free ingest and real-time analytics. Ideally, a distributed architecture of some sort. It also needs to have support for full API calls through stored procedures or anything similar that allows full support for API calls. Data store should have the ability to store old data as well as new data and be able to join between the two within strict SLAs and without really extrapolated costs. Additionally, the data store aspect of the solution would support multiple ingest formats, being JSON, CSVs, Parquet, or whatever it needs to be, at the same level of ingest efficiency and speed. And finally, the data store should be easy to manage, support, and operationalize. Now, this slide is showing a potential solution of what can be used to satisfy the requirements of COVID-19 contact tracing. If we look closely, we can map the blocks in the architecture to the components we discussed in our previous slide, in our two previous slides. The browser part of the solution, or the purple block on the lower left, is usually the visualization dashboard that's used as a front-end interface for the users to interact with the system. The visualization calls are made to the rest of the system using a web server and an API provider of some sort that allows the visualization tool to make API calls to the rest of the system. Excuse me. The green block on the upper left of the architecture is the data ingested into the cluster, being the telco location real-time data, historical data, or a mix of both. It can also be the health department's COVID-19 patients data as needed. The location data can be in multiple supported formats, in this case being Parquet files, which are known to work very well with parallel data loads at high concurrency rate. The heart of the system really lies within the data store part of it and its capabilities. The decision of using MemSQL here is based on the unique requirements of the solution and how MemSQL can perform in each and every one of them. MemSQL pipelines can be used to stream telco and patients' data into the system at a very high rate and extreme efficiency using a distributed and parallelized fashion. MemSQL support for geospatial data is a main requirement for this solution, and MemSQL not only supports geospatial as a data type, but it's a first-class data type, meaning that full join capabilities can happen against the geospatial data being stored. MemSQL is a powerful time series data store, meaning that it can always support a moving window of analytics. Because if you think about it, we're analyzing a moving target, in this case being a COVID-19 patient. Finally, MemSQL's column store can be used to store the petabytes and petabytes of reference data at a very low cost and high performance efficiency using MemSQL's single store capabilities. Last but not least, the solution can obviously sit in any cloud vendor environment and it can also sit on-prem. In the next slide, let's touch more on MemSQL's unique capabilities. I think a question is, what else can MemSQL do besides the things that we've already discussed in terms of capabilities? MemSQL is simply a modern distributed operational data platform which combines the familiarity, consistency, and durability of an RDBMS environment with the flexibility and scalability of a NoSQL environment. As we've explained it, it allows you to run analytics against geospatial data at a very high rate of concurrency and efficiency, being in the SQL or NoSQL format. It can modernize legacy data platforms and it can integrate well with AI and ML. It's fully MySQL wire compatible, which allows it to run anywhere where MySQL would run. It can be either schema and or schemaless, and it combines the capabilities of running full relational models as well as NoSQL-oriented models using JSON key value pairs or documents. It can also support a very high rate of data ingest using MemSQL's unique pipeline functionality, as well as change data capture capabilities in both a heterogeneous and homogeneous fashion. Additionally, the distributed shared nothing architecture of MemSQL allows lock-free scalability and concurrency. Finally, MemSQL can run anywhere, be it on-prem using commodity hardware or fully managed in a private cloud environment through our Helios Managed Services offering, or it can be a combination of both as a hybrid model. MemSQL can also run in containers, which makes integration into existing Docker or Kubernetes ecosystems near seamless. The final diagram is just to illustrate a simple MemSQL architecture, which usually consists of multiple nodes, one of them being the master node. Some nodes are responsible for receiving client connections from a load balancer and act as an intelligence query router that runs queries using a distributed optimizer. Those same nodes can be used to perform DDLs and DMLs, and they don't usually hold any data. The master node is ideally responsible for cluster monitoring and operations. And finally, the MemSQL nodes depicted on the bottom of the architecture there hold the data that is shared or that is sharded across partitions, which provide redundancy for high availability. And those nodes are used to run the queries that are then aggregated and returned to the user. Last but not least, let's not forget that one of MemSQL's unique advantages is that it can run on any commodity hardware with no fancy storage or server requirements. Thank you for listening, and please let me know if you have any questions.